we've seen that x of t equals a cosine of omega t plus theta naught is one general solution to the equation x double prime of t equals negative k over m times x. And omega is the square root of k over m. Now before we had c here, but I'm going to revert now to using a, because a is going to stand for the amplitude of the motion, as we'll see in a minute. Now the unit circle interpretation of this function is fairly straightforward. We have a vector, and the vector traces a path around the circle following what we've called the reference point. The vector is r of t, and r of t is a cosine of omega t plus theta naught I plus a sine of omega t plus theta naught j. Now these are the I and j vectors, not the square root of negative 1. So here's our r of t. Now the motion of the oscillator on the x-axis, if we're going to use the x projection, a cosine of omega t plus theta naught here, with this function, the x projection is this function. Okay, so here's the r of t vector, here's the x of t vector, which is the vector projection of the r of t vector onto the x-axis, and x of t is the I component of r of t, and the I component is this. Okay, so the r of t vector is following a point around the circle. The point's moving with angular velocity omega. So reference point moves at angular velocity omega. So there's your reference point. We have the tangential component of the velocity. So we have a v of t vector. And I'm just looking for a place to label this. Again, I didn't leave myself much room. It's kind of small, but I think you should have good enough resolution to see this. There's your v of t vector. And we also have an a of t vector. Again, things are a little crowded here. A is the radius, the magnitude of the r of t vector. So the circle has radius a. So the main thing you want to see is the r of t vector with its projection onto the x-axis of x of t, the v of t vector, and as we've seen before, that has an x and a y component, or an I and a j component, and the I component is going to be the velocity of a point on the x-axis that follows this reference point as it goes around the circle. The projection of the reference point is the point on the x-axis. That point is at position x of t here, has velocity, which would be vx of t, the x component of the v of t vector, and acceleration, we could say a sub y of t, the x component of the a of t vector. Now all that follows from this position function, because if we take the derivative of this function, which is the same as this function, we're going to get the velocity function, and that's going to agree with the x component of this velocity vector. A second derivative of this function will give us an acceleration vector, which will agree with the x component of this a of t vector. That's a little bit hard to see here. Now, the only thing we haven't described, a being the amplitude, omega being the square root of k over m, is this theta naught. Now, if t equals 0, then we have a cosine of theta naught. Okay, we're going to have an initial position, an initial t equals 0 position of the oscillator. It doesn't have to start from here, doesn't have to start from here, doesn't have to start from here. It can start anywhere. So that's as good a point as any. So if it starts from here, and if it starts from here, there's the initial position, and this means that the initial position of the reference point has to be either here or here. Now, if the initial position of the reference point is here, and if omega is positive, then the point's moving around the circle like so. And, excuse me, we see that the velocity vector up here is going to be out in this direction, so that its horizontal component is going to be in this direction. If it's this point, if this is the initial point on the reference circle, then the velocity vector is going to be in this direction, and the object will be moving in this direction at the initial instant. So if this is the initial position, we're either going to have an initial velocity in this direction or this direction, depending on whether the point is here or here, whether the point on the reference circle is initially here or here. Now, what this allows us to do is accommodate this model for any initial condition. We can start the oscillator at any point between here and here, and we can give it a velocity that's either to the left or to the right at that point. For example, we might have an oscillator on a spring. It's going to have an amplitude of motion that takes it all the way out to here, but it's initially, let's say, right here, and we give it a whack at this point. Okay, well, that starts it in motion in this direction, and that motion could well follow the model of this circle. If that motion ends up with amplitude A, then we will follow the model of this circle. Or we could give it a nudge in this direction. We could whack it in this direction, and then it would have, then our initial point would be here. Now, what does that have to do with theta naught? Well, it has to do everything with theta naught. Theta naught, if we are at this point, and I'm going to choose that point because the board's a little less cluttered up here, it's going to be a little easier to label. And this, unfortunately, this looks like it's an extension of this. This is not necessarily 180 degrees out of phase with this. Okay, could be here, could be here, could be anywhere. I just made an unfortunate choice of the initial position and didn't realize that was going to happen. Okay, well, this is theta naught. That is the initial phase. So that at that point, the x component is a times the cosine. Well, t is 0 at the initial point, so it's going to be a cosine of theta naught. And what do you have? Well, you have length A here, you have angle theta naught. The projection is here. That's at a cosine theta naught. So x equals a cosine of theta naught. The initial position, x, determines the angle theta naught. Well, it determines two possible choices. The other choice is down here, and the theta naught would be all the way around here. So, of the two choices, the initial direction of the oscillator determines whether we use this choice or this choice. If we use this choice, then the initial direction will be this way. If we use this choice, then the initial direction will be back this way. So now let's write that down. Initial x position determines two possible choices for theta naught. Okay. And the initial direction of motion determines which of the two choices. So that the initial x position and the initial direction of motion tells you what theta naught is, okay? Theta naught, well, x equals a cosine theta naught, so theta naught equals the inverse cosine of x over a. Well, not just this. Okay, theta naught could be the inverse cosine of x over a, or it could be 360 degrees minus the inverse cosine of x over a. You'll notice that I also changed the color of the A of t vector and the labeling of it. Still not sure that's all that legible, but this says A of t. That indicates the radial acceleration vector, the acceleration vector back toward the origin. So, our reference point, as we've pointed out here, follows the circle, and here's the equation of motion in 2 dimensions of the reference point. The velocity vector can be obtained by reasoning out the speed, which will be omega times a, and using the sines and cosines and the fact that this is going to be 90 degrees ahead of the r of t vector. The acceleration 90 degrees ahead of that. Or we can get the same thing by taking derivatives. I didn't specify how we got these. All these vector functions that describe the position, velocity, and acceleration in 2 dimensions of the reference point can be obtained either using calculus by taking derivatives or by reasoning out, as we've done in the past. So I'm not going to go through that reasoning again. If we're talking about modeling the motion of an object on the x-axis, then the projections of these 3 vectors onto the x-axis give us the velocity, the position, velocity, and acceleration of the actual oscillator. So that here would be the position, here would be the velocity, here would be the acceleration. We could as easily have used the sine function for the position function. Now, of course, on the unit circle, the sine is vertical, but there's no essential reason to use the cosine for the x and the sine for the y when you're actually modeling a simple harmonic motion. Either function will work. The sine function, of course, at t equals 0, starts at a different position than the cosine would, so you would have a different theta naught. You can work out those details. I don't want to go into too much detail on that right now because we'll lose the thread. The only difference between this function and this function is that the theta naught would be different. The theta naught is going to differ by 90 degrees between a cosine and a sine function because one of those functions is 90 degrees ahead of the other, and the other, of course, is 90 degrees behind that one.